and there is a joint work with Professor Favata and Professor Vidoli from the University of Rome, and Professor Corrado Maurini from the Sorbonne University. So a brief outline of the next slide. I will start with the motivation of the work, presenting a little bit of historical background. I will present a physical model that tries to account fatigue. Its implementation and some preliminary numerical results, and in the end, I will conclude with some remarks. Okay, so what about it? So this slide is dedicated to the Paris Hertonian law. That is actually Paris law that is actually an experimental law that describes very well the material behavior in the long run. So when the body is subjected to a cyclic load. So it makes in relation mainly two things. The crack broke with the stress intensity factor, and it's a power law where this is called Paris exponent. In the next slide, actually, when I'm talking about the Paris law, I will refer to this form of it, that is actually, where here T is a macroscopic time that try to average the small oscillation that is happening during this time. Anyway, is proportional to the number of cycles. G, instead of the stress intensity factor, use this ratio, the energy release rate over the non-dimensional with respect to the toughness of the material. And this is the exponent. The energy release rate is related to the stress intensity factor by the power of 2, and so this coefficient is basically 1/2 of this one. If you do like an experimental campaign on a material subjected to different ambient cyclic loads, you will obtain on the log-log plot this continuous line. And basically, the Paris law works very well in the region B, and this continuous line is basically approximated by the straight line with slope m. As soon as the energy release rate goes in the direction of the toughness of the material, we obtain basically the asymptotic behavior is basically the structure, and we have also this regime that basically say that there's another setup here that if let's say to you that the energy release rate is too slow, basically you cannot any propagation of the sorry. Okay. A fun fact about the original paper about Paris Erdogan is that they did a very interesting campaign, experimental campaign, and they organized the data that they obtain they gain in the log-log plot, and it's nice because in the paper they were so tempted to draw a straight line between the data, but this paper actually dates back to 63. And only 50 years after, we have a sort of analytical justification of the Paris law of the works of Marigot and co-workers, where for the first time they prove a link between the fracture and the fatigue. And the main ingredients of these works are the following. So you need basically a sequential minimization of the total energy under cyclic loads. You need to take into account like a cohesive surface energy, and of course you need the reversibility that permit to your crack to go, preventing the healing of it. So let's move to the second part. So the question right now is it possible actually to obtain the Paris law from a variational setting? So what I'm asking to you is to consider this minimization problem, where our unknown field is the crack length at the time capital T, and so our energy as usual. So we have a potential energy here, and here a distribution potential that in this case is function of the length that we're going to find, and as a sort of memory because it takes also into account the crack length at the time capital T I. That is the previous basically time step. So this minimization problem is actually subjected to this constraint. that is the irreversibility constraint. So in order to find the minimum, we have to consider the Karash-Tucker condition, and we have to impose the derivative of this energy with respect to the internal parameter equal to 0 in order to get the crack growth. So let's compute this. Here is the computation of this derivative, and by definition, the energy release rate is the opposite of the potential, the derivative of the potential energy. And finally, we can find the first hint in order to determine this function that related this ratio, the energy release rate with respect to the toughness of material with the first derivative of this function. So this ratio is actually is also showing up in the Paris law that I'm recording here. And if we, of course, if you notice these two constants, we can recast them in another constant that we call length of that as a measure of the length. And by isolating the term G over GC, we obtain this, but from what we have obtained in the previous slide, G over GC is also related to the first derivative of this function D. So we are able finally to find this function D, that is nothing but the power law of function of the crack length at this macroscopic time minus the crack length of the previous time step. So I'm not spending so much time on the well-known phase field approximation of Vidoli fracture, due to the fact that Camilla did a very great presentation. But here you have the potential energy, and here the dissipation energy, and you are actually minimizing this function with respect to displacement and the damage field. And I want only to note that this calligraphic has basically the meaning in the phase field of an approximation of the measure of the crack set, so the Hasselhoff measure that in 2D is basically the length, is an approximation of the length of the crack. So what we conjecture is that modify this part of the functional with the function that we just characterized in the previous slide. So basically this D is not only a function of the measure of the crack set that we want to find, but also as a memory of the crack length in the previous time step. Okay, so we have implemented in Phoenix X platform is functional, and here are some results that I have to move because the links doesn't work. So if I remember well, something like that. Okay, sorry. Okay, so basically, first description. Basically, this is the sample that we are testing. We are trying to recover the fatigue mode 1. We set the Paris exponent equal to 2, and we apply a symmetric boundary condition here. This sample has already a pre-existing crack set here. And we actually, so we changed the boundary condition, but we changed them in order that the energy release rate is very, very small with respect to the toughness of the net energy, in order to stay in the regime where the Paris law actually works. And so sorry, just a very brief video of the simulation, where you actually can, of course, you can see that at each iteration you find the crack that is growing to the end. A little more. Oh, okay. And we collect. We did different simulation with different boundary condition, and we collect them. The color bar here represents the magnitude of the displacement that we have imposed. So the most severe one is, for example, this that breaks the sample into 12 iterations. And if you plot on the log plot the data, you see that actually the interpolation function has a slope equal to 2, that is the parameter that we impose. So here a little bit more complex case. So we want to, here is a mixed mode 1 and 2. again, we impose the exponent equal to 2, and we apply the boundary condition of the energy release rate. It's really small in comparison with the toughness. So here there is a slide, and here there is already a persisting crack. This lamp is pushed up with this displacement, and this is actually an asymmetric boundary condition, because you cannot see really well, but this is not equal to u, but is a reduction of u by the function by a coefficient phi. So, for example, in this case, it's 0.8, and so let me show the video simulation. So basically, what you get. Okay, so what you get is the straight line beginning. It's quite fast. As soon as it curves, the graph of course slow down, because that's all. I'm still here. Okay, so sorry, it's so no, and basically. Here it's only these dots actually represent the results that we had at each iteration, and also it's still a lot of plot. And you have that the interpolation light has again retrieved again the coefficient, the Paris exponent. Okay, I think. Okay, so I can talk about this one also. So, like, there is actually some open problem in the sense that this capital S is, yes, the measure of the crack, but if you have to crack, is the measure of both of the cracks. So, due to the fact that D is not actually linear, so you cannot split it this way. So you have to take into account each region in a different way. So by modifying again the dissipative part of the functional, by taking into account the sum of each measure crack set. And okay, so here the last video, I promise. Okay, is this. So here, okay, so you're two different. So before I didn't mention, but I show you the damage field that was evolving through the iteration. But here you have also the displacement. Don't worry about that. I mean, it's just, I mean, so it's okay. So again, so here that is the displacement field in the y direction, and basically that's been that this element it's not commuted anymore with this one. So it's basically good. Okay. Okay, so in conclusion, yes, in conclusion, we have recast the Paris law in a variational setting. We presented a modification of the phase field for the triple fracture, accounting for the fatigue in this way, and we show some result, preliminary result, and its implementation. So these are some content info.
Thank you, Andrea, for the presentation. Very nice. Thanks. And yeah, now you have the chance to ask questions. Are there questions? Yep.
Can you show again your dissipation function as function of crack length?
Yes. Sure. Oops. It was a secret. You mean this one?
No, there was something before where you have a power function.
Yes, maybe. Are you referring to this one?
Maybe. So
maybe
x here.
X here is the. In this case is the difference between the two lengths. Sorry.
Yeah. So it's the crack extension basically.
Is the difference? It has actually this function has the capability to have a sort of memory of what happens in the previous step.
Yes.
Okay.
So why do you take the power law?
No, it comes out from the calculation, and it's not that. So from here, so delete this term, and you get this relation. Okay. And you have the derivative, and you want to find the function. So you just integrate terms. This is just a recasting in variable of what it shows here integrated. It's just like some calculation. If I want, I show you after the presentation. I didn't invent it. It's something that comes up by defining this. Okay?
Well, physically, I don't understand why the dissipation should increase when the crack size increases.
No, it's because it's not the crack size. It's the difference between it's the evolution. It takes account the difference between the crack size now minus the one before at the time step. Okay.
So it's the crack extension.
Yes, it's the relativity. The relative crack extension is relative to the previous time step. So, for example, if it's really hard to see from here, but imagine you can actually retrieve from this function actually the Griffith model, in the sense that Li, due to the fact that as soon as you reach the toughness of the material, you don't have an Li. It's basically it's zero, and you have all the crack extension in one iteration. Okay.
Is it the initial crack size in one cycle? At the beginning, the crack size at the beginning of the cycle?
In Griffith case, yes.
Yeah, but we are not in the Griffith case.
No, exactly. That's why there is. So this is our known. This is something coming from the iteration, the previous iteration. Okay. So it's not growing. It depends of the difference between these two terms. So, like for example, I show you a case where I apply this formula and you. Sorry. Okay. In this case, for example, the difference here. For example, so this is time step 1. This is time step I don't know, the last one. And you see that here is there is the log of the difference between the extension of the cracking, the relative extension of the crack, and you see that the velocity is slowing down while we are increasing the time step. Okay.
Okay, maybe
we should discuss about the
okay.
It is really not clear to me.
Yeah, so maybe I would suggest to continue the discussion in the coffee break because we are running out of time. So then, thanks again for the. Now we have the next speaker, and now I guess we have to be strong because we will see fracturing bones. The next speaker is very. So the next speaker is Maxime Levy, and he's also part of the NewFrag team. And he is at Tel Aviv University, and today in his presentation he will speak about a preliminary phase field implementation for bone fracture, considering heterogeneous elastic and fracture properties. So, please.